All right, so last time we did a couple of compound inequality, or really one, same problem but with an and with an or, compound inequality. And so we're going to continue. We're just going to look at some more examples here. And so let's take a look at number 2, and we're going to do something similar here. We're going to do a part A and a part B and kind of just compare the two. So this time, let's say we have, again, we're starting with some pretty simple linear inequalities to solve. So 2x plus 18 is less than 0, or 4x plus 1 is greater than negative 11. So here I'm just really trying to get us to focus in on not really the complicated solving, but more just like, what does this word mean? Alrighty, so let's jump in, and we just need to do a little bit of solving, just solving these linear inequalities here. So in the first one, we're going to start by subtracting our 18. So 2x is less than negative 18. In the second one, we subtract 1, so 4x is greater than negative 12. Remember, you don't reverse your inequality for subtraction, and you don't reverse it for division unless it's division by a negative, and we don't have that here. So this time, the inequalities, everything just stays lined up. We divide by 2 in the first one, we get x is less than negative 9, or in the second one, dividing by 4, x is greater than negative 3. All right, so again, I want you to think about your work as just on any of these initially being, let's just think about what this graph would look like as we graph these. All right, so let's say I graph here and I'm looking at negative 9, we'll say, is down here. So here's my negative 9. And the first one is everything is less than the negative 9. So I am shading everything to the left of this negative 9. And of course, we have to be real clear what's happening at the negative 9, not included. So either open, ooh, that one got away from me, either open parenthesis or open circle. And then let's say we have our negative 3 would be somewhere over here to the right. So here's my negative 3. The second one is saying x is greater than negative 3. So this would be shading everything to the right of negative 3. Again, not including the negative 3, so either open parenthesis or open circle. All right, now I need to think about, with the word or, we should be thinking to ourselves, or means union, means take all of it. So when you see or, I want you to be thinking, this is where we're thinking to ourselves, that's supposed to say all, but we take all of it. So union, anything that's in either the first set or the second set. So all of it is going to be anything in that first set or anything in that second set. So in this problem, when you just graph them both on the number line, that really does become our final answer in this one. But that generally is not the case. So it's always just kind of graphing both of them and then thinking about what the word means. In this case, it just so happens that when I take all of it, it's just everything that's there. So it would have been everything less than the negative 9 or everything greater than the negative 3. So my final answer is really the exact same thing in this case. So I'm just drawing it again, just to emphasize, like, yes, we actually thought about the word, and the word here was or, which means takes all of it, and that's just what we're looking at right there. All right, let's write this out in interval notation. So no smallest value, so we start at negative infinity, always a parenthesis with the negative infinities, up to negative 9. Now, with interval notation, we don't write the word or, we say union. But remember, this is all synonymous, or synonymous with union. And then we pick up the next set at negative 3. It never ends. It goes off to infinity. So that is my final answer, both as a graph and as the interval notation there. Okay, now part B, let's think about the exact same inequalities, but suppose my word this time was and. So again, we've already solved these, so I'll just say dot, dot, dot. We know we get x is less than -9. We know we get x is greater than -3. This time, though, it's the word and. Again, the initial work would also be the same as the work that I have shown up above, meaning we're just initially thinking about what both of these would look like if I graph them. So I'm thinking about, what does everything less than -9 look like? There it is again. And then what does everything greater than -3 look like? Okay, here's that one. And now after we do everything the same, now we think about the word. The word is and. And is the intersection, or what I want you to think of then as the overlap. So what got shaded twice? And as we look at this one, nothing got shaded twice. There was no overlap. Nothing is both yellow and red in that shading. So when there's no overlap in this case, our final answer would be an empty number line if we had to graph it. But the final answer is really no solution. And no solution, we would say, is the empty set. And the empty set gets denoted with 0 with like this slash through it. And that means no solution. That's another good reason for me to mention right here. This is why you don't use that 0 with a slash through it as your 0, because that would be very different than saying the empty set. All right, so no solution on that one. There was no overlap if we use the word and. All right, let's look at another example. So this is like our third example in this group. Let's look at a compound inequality where it's already implied that the word and is in place here. This is the kind of thing we actually would have solved in basic algebra, but we wouldn't have talked about compound inequalities like in terms of the and the or. We just explain it as saying, guess what? When we're solving a compound inequality like this, 1 less than or equal to -2/3 x plus 3 less than 4, we're really saying that both the first inequality has to be solved and has to be true, and at the same time, the second inequality has to be solved and has to be true. So it really implies, though we don't need to break it up, when you see an inequality this way, it's really saying that both the first one and the second one have to be true. But when they have this center in common, we can do it all at once. Meaning, if I'm trying to, my goal, let's scroll back up for a second. In our opening examples, let's think about on the very first page when we were focusing on notation, we're really looking at something like this example number 3. We're trying to get like this x here in the center all by itself. That's the kind of compound inequality we have. We have an expression in the center, 2 numbers on the outside. So our goal is to get x by itself in the center. So that's what we're doing here. So if I'm trying to get x by itself in the center, anything I do to the center, I need to do to both these inequalities that I'm solving. I'm solving this left inequality and this right inequality at the same time. So I subtract 3 essentially from all sections, let's say. All right, 1 minus 3 is -2, is less than or equal to the -2/3 x is less than, and then the 4 minus 3 is equal to 1. Now, you could get rid of this fraction in one fell swoop by multiplying everything through by the reciprocal of -3/2. And that's probably the quickest and most direct way. But if that isn't so comfortable for you, maybe you first just recognize I want to get rid of first just the denominator. I'm going to get rid of the 3. So if you want to do it in 2 steps, you can. You can multiply, again, kind of all three parts here, we can multiply everything through by 3. So on the far left, we have negative 6 is less than or equal to, in the center, negative 2x, and then on the far right, we have 3. And now our last step here to get x all by itself in the center is to divide by negative 2. And this action of dividing by a negative on what's really both of these inequalities at the same time, remember what that means. That is where we have to reverse the direction of our inequalities. All right, so on the far left, we now have 3. In the center, of course, I have my x, and on the far right, I'm going to have this negative 3/2. Okay, now that is perfectly mathematically correct. It's saying 3 is bigger than or equal to my answers, x, is bigger than negative 1 1/2. But sometimes it's nice, rather than writing it from greatest to least, let's just observe that this is the same thing if I wrote it from least to greatest. So if I started kind of down here from the perspective of the negative 3/2 and then go in this direction, that's kind of what I'm doing here. So I start with my negative 3/2. That inequality points towards the negative 3/2 and opens out towards the x. The next inequality points at and opens out towards or equal to the 3. So those two are the same thing, and sometimes it's kind of nice to see it instead of from greatest to least, to see it from least to greatest. All right, let's look at our graph. So our graph in this case, so negative 3/2, maybe somewhere over here. If you want to think of it as negative 1 1/2, you could. And then maybe somewhere over here is, I don't know. Obviously, this isn't exact 3. Somewhere in the middle there, somewhere is a 0. All right, and these are all of the values. The nice thing about this compound inequality as we look at it is it's, I think, maybe a little more kind of clear what we're looking at here. It's everything that is sandwiched in between these values. So as we're getting ready to look at our answer, all of the x's that are bigger than the negative 3/2 and less than or equal to the 3 is just everything sandwiched in between. Again, just being careful to show the open parenthesis or open circle at the negative 3/2 and the inclusion, meaning the square bracket or the filled in circle on the end with the 3. And our interval notation, parenthesis, negative 3, comma, 3 with a bracket. All right, one more here. All right, and we're just going to do one part on this one. We won't do the thing where I'm always doing the and the or. So we're going to have kind of two separate ones this time. Negative 2x minus 4 greater than or equal to negative 6, or 2 quantity x minus 3 is less than 0. Okay, let's solve them both. All right, so the first one, let's start by adding our 4 to both sides. So we are going to have our negative 2x is greater than or equal to negative 2. And then to finish solving for that x, I need to divide by the coefficient, and that coefficient is a negative 2. So this action of dividing both sides by negative 2 reverses my inequality. So I now have that x is less than or equal to 1. Or, solving the inequality on the right here, I need to start by distributing through my 2. So 2x minus 6 is less than 0. And then I will add my 6 here to the other side. And so we'll have 2x is less than 6. And then just dividing both sides by the 2. Haven't divided by a negative, so keep everything as it is. X less than stays 3. All right, so you know the drill, hopefully at this point. My work is simply to graph both of them on the same number line. And so, I don't know, let's just say here is 0, let's say here's 1, 2, and somewhere over here is 3. Okay, so let's give this a whirl, and let's start with x is less than or equal to 1. So x less than or equal to 1, which is everything smaller than, so to the left of the 1. So here's everything less than the 1. So to show the or equal to, I'm going to put my nice square bracket there on the 1. Okay, now the or, but then x is the second one I want to think about the graph of it, is the x is less than the 3. So now let's take a look at 3. Again, it's a less than. So again, I'm looking at shading here to the left of, and it's to the left of the 3. Okay, so again, this is everything going left of the 3. Again, I don't want to include the, or I shouldn't say again, this time I don't want to include the 3, so a parenthesis here. All right, so what do we think about when we use the word or? Well, or is synonymous with union, and so or means we take all of it, anything that is in either the first set or the second set. So all of it here is all of it. So if it had been and, so just as a quick comment, if it had been an and would be the overlap, it would have just been this part, everything up until the 1, everything that got shaded twice. So if it had been and, that would have been our answer, but this one is just doing the or, and so our final answer, anything that got shaded at all, anything that was in either the first or the second set, is going to look like this, everything that's less than the 3. So this is everything. So what I want you to be careful of is sometimes, and I think this will happen more, especially as we move into the next section, sometimes people start to fall into a bad habit of assuming that every single or problem is going to be like two ends of a graph shaded out in opposite direction, and that every time we have an and, it's like what's in the center. And that won't always be the case, so you really have to think about just kind of what both the inequalities are and then what the word is telling you. You can't assume that, oh, or is going to go out in opposite directions and is going to be the center, and here's a good reason why. All right. Next time, 9.2, we'll get started looking at absolute value concepts related to equations and inequalities, starting with, of course, you can see there at the bottom, absolute value equations is what we'll look at next time.